Good day, everyone. Welcome back. I hope that you've had a nice couple of weeks off and had a wonderful Christmas with your friends and family. This is the first lesson in the final unit of Math 10C. This final unit is dealing with what we call linear systems of equations, and this is lesson 8.1, which is titled Systems of Linear Equations and Graphs. The 8.1, of course, refers to the textbook section that this lesson is modeled after. So if you need additional support in this particular topic, then you can refer to the textbook for more sample problems and practice. What we're going to be looking at doing today is solving systems of linear equations using a graphical approach, and that includes graphing on paper by constructing a graph using what we learned in the previous unit about slopes and y-intercepts. And it also includes getting to know our graphing calculator a little bit better so that we don't have to do it on paper all the time. So if we're just after an answer to a problem, we can just go to the graphing calculator and get it. Of course, if I had a written response assignment or exam question where I asked you to construct the graphs, you'd be expected to do so on paper. We're also going to be taking the solution to a system of linear equations and verify that solution by substituting the answer we get back into the original system of equations. And all of this really doesn't mean much to you because you don't really know what a system of linear equations is yet. So that's where we're going to begin today. This lesson is on page 1 of your unit handout, and you will need a ruler for at least one of the problems. So we're going to define something first of all. A system of linear equations is a group of linear equations with common variables. And you can have a system of linear equations that has two linear equations, or you can have a system that has more than two. In Math 10C, we're going to limit our experience to systems of linear equations that contain two equations that have common variables. If you find yourself taking calculus or post-secondary mathematics or post-secondary science, either physics or chemistry, you'll find that occasionally you may encounter systems of 3 or 4 or maybe even 5 linear equations. But in this course, this would be a good example of a system of linear equations. You have 3x minus y equals 4, which you should recognize as a linear equation from the previous unit. And what that means is if you were to graph that relation, 3x minus y equals 4, you would get a straight line. And we have another equation in this system, which is x minus y equals negative 2. Again, it's a linear system of equations because both of those equations are linear. In other words, both of those equations, if you were to graph them, and we will, you would see that they're straight lines. So what is the solution to a system of linear equations? Well, the solution to a linear system, or a system of linear equations, is an ordered pair that makes both equations true. Now, what is an ordered pair? An ordered pair is a pair of numbers where one of the numbers is x and the other number is y, and they are locked together, and that means if you plot them, they are a point. And if I were to graph both of these equations, I think it's important for you to understand that there are, on each of the lines we would get, an infinite number of points, which means there's an infinite number of ordered pairs that make the first equation true. There's an infinite number of ordered pairs that make the second equation true. I'll give you an example here. And I'm not going to write anything down here, but if you put 1 in for x and negative 1 in for y in the top equation, you're going to have, well, I'll show you what you would get. On the left-hand side of that top equation, if you put in 1 for x, we would have 3 multiplied by 1, minus, if I put in negative 1 for y, I would get 4. So 1 comma negative 1 is a solution to that top equation. If I were to put in 2 for x and 2 for y, what would we get? We'd get 3 times x, which is 2, minus y, which is 2. We also get 4. So I could go on, but the point is there are an infinite number of pairs of numbers that make that top equation true. And there are also an infinite number of pairs of numbers that make the bottom equation true. What this statement at the bottom of your screen is saying is the system has a solution that is an ordered pair that makes both equations true. And sometimes what we like to say is that that ordered pair satisfies both equations. It makes both equations true. So as a warm-up, we're going to use that system of linear equations that I've described in the definitions above to answer the following questions. First of all, show that the point 4, 8 makes equation 1 true, but does not make equation 2 true. Well, let me write down equation 1. But I want to make a very important point here. When you're trying to demonstrate that an equation is true in math, you leave out the equal sign, and you simply draw a vertical line. I'm also going to write down equation 2 over here, which is x minus y. And the right-hand side is equal to negative 2. So we write down what the left-hand side is equal to, we write down what the right-hand side is equal to, and if I want to decide whether this first equation is true, it's going to involve some substitution. It's going to involve me taking this number 4 and putting it here for x, and this number 8 and putting it here for y. And that vertical line between the 3x minus y and the 4 is something that you're not supposed to cross. I'm trying to actually build some skills here in your repertoire that are going to be important for Math 20, but mostly for Math 30. So we're treating the left and the right-hand side separately. That's an important idea. Well, let's just simplify what we have on the left-hand side here. We have to substitute in first 4 for x and 8 for y. Now we can simplify that. 3 times 4 is 12. And then we have minus 8. 12 minus 8 is 4. And now we can see that the left-hand side and the right-hand side are equal. So what we have shown is that 4, 8 makes equation 1 true. Which means 4, 8 is a solution to equation 1. By the way, there's an infinite number of solutions to equation 1. Now let's do the same thing for equation 2. Again, wherever we see an x, we're going to put the x coordinate in the question, which is 4. And wherever we see a y, we're going to put the y coordinate, which is 8. So I get 4 minus 8, and I subtract 4 minus 8 and get negative 4. And clearly, the left-hand side and the right-hand side are not equal to each other. And that's what we were asked to demonstrate. We were asked to show that equation 1 is satisfied by 4, 8, but equation 2 is not satisfied by 4, 8. Which means 4, 8 is a solution to one of the equations but not the other in this system. And that means that 4, 8 is not a solution to the system. If a point is a solution to the system, it has to make both equations true. Warm-up number 2, show that the point 5, 7 makes equation 2 true, but not 1. So let me rewrite the equations. I've just got them here so I can refer to them. Equation 1 is 3x minus y on the left-hand side, and on the right-hand side is 4. Equation 2 is x minus y on the left-hand side, and negative 2 on the right. This time our x coordinate is 5, so wherever we see an x, we're going to put a 5. Our y coordinate is 7, so wherever we see a y, we're going to put a 7. All right, what happens with equation 1? We have 3 times 5 minus 7. That's 15 minus 7, which is 8. The left-hand side is 8. The right-hand side is 4. The left-hand side is not equal to the right-hand side. So the point 5 comma 7 does not make equation 1 true. Okay, what about equation 2? Well, the x-coordinate is 5 minus the y-coordinate, which is 7. 5 minus 7 is negative 2. When I cast my gaze up to what the right-hand side is equal to, it's also equal to negative 2, which means that the left-hand side and the right-hand side are equal. Now, I want to point something out to you, that when we say, well, I'm just going to jump ahead here. When we say that 4 comma 8 is a solution to equation 1, so this is a summary of everything, and you don't need to write anything down. When I'm saying that 4 comma 8 is a point that is a solution to equation 1, since equation 1 is a linear function, and that means equation 1 can be represented by a line drawn on an xy coordinate grid, I'm telling you that 4 comma 8 is a point on that line. I mean, think about that for a second. Values of x and y that make an equation true, that make a linear equation true, will be points that are on that line. Well, 4 comma 8 cannot be a point on line 2 because it didn't make equation 2 correct. When we look at 5 comma 7, 5 comma 7 did not make equation 1 true, so it's not a point on the line 3x minus y equals 4 because that's equation 1. 5 comma 7 was a point that made equation 2 true, so it is a point on the line described by equation 2. But you really need to roll this around in your head, I think. A solution to a linear equation is an ordered pair that makes the equation true, and if that's the case, it is a point on the line. And that's why I said earlier, linear equations have many solutions. All you have to do is find a point on the line. That leads us to a question. If I'm going to tell you now there's only one ordered pair that makes both equations true, how can we find it? Well, it would have to be a point that's on both lines. If you were to graph equation 1, you'd get a straight line. We know that from the previous unit. If you were to graph equation 2, you'd get a straight line. Every point on line 1 is a solution to equation 1. Every point on line 2 is a solution to equation 2. So the only way you can get a solution to both equations is if it's a point that's common to both lines. And that means it's wherever both lines intersect. So here's what we're going to do. We're asked to graph both of these equations. Well, the first thing we have to do is rearrange them for y. My first equation can be rewritten as 3x equals y plus 4. All I'm doing there is I'm adding y to both sides. If you need to see that, I'm just saying plus y. And then if I subtract 4 from both sides, equation 1 becomes y equals 3x minus 4. Doing the same bit of business with equation 2, I'm going to add y to both sides. I just prefer the y's to be positive. And that takes me to this statement, that x is equal to y minus 2. And that means if I add 2 to both sides, I have y is equal to x plus 2. And I'm just going to put in brackets here beside equation 1 in case you've forgotten. This tells us the slope is equal to 3 and the y-intercept is equal to -4. I'm looking at y equals mx plus b, which is why I rearranged those two equations for y. For equation 2, the coefficient of x is the number 1, which means the slope of equation 2 is 1, and the y-intercept is 2. So to graph these is really pretty simple. As I said, you're going to need a ruler. Starting off with equation 1, I'm going to plot the point on the y-axis of -4. This is the y-intercept. The slope is 3, which, if you like, you can think of as 3 over 1. And that means we go over 1 and up 3 from that y-intercept. Over 1, up 1, 2, 3. Over 1, up 1, 2, 3. Over 1, up 3. So you'll lay your ruler down. Draw your line. And just before we go on, I want everybody to understand that every single point on this line, I want to get rid of these little tiny dots. I don't want you to think that that's part of the graph. Every single point on this line, any of these points, and there's an infinite number of them, they are all solutions to equation 1. And this line goes on forever. Any point on the line is a solution to that equation. Let's do the next one. The next one has, for equation 2, a y-intercept of 2 and a slope of 1, which means the number 1 is 1 over 1, which means you go over 1 and up 1, over 1 and up 1, etc. Oh, well, we've just hit it. I'm going to complete the graph. You don't need to draw all of these dots. I'm just choosing 2. So this is line 2, which is representative of equation 2. This is line 1, which is representative of equation 1. And this point is a common point. It's a point of intersection, which means that it is a solution to equation 1 and equation 2, and the coordinates are 3, 5. So the solution to this system is x equals 3, y equals 5. Or we could say 3, 5. Now, the system of equations had this equation, 3x minus y equals 4. And it had this equation, x minus y equals -2. If we put in x as 3 and y as 5, we get 9 minus 5. Whoops. We get 9 minus 5 equals 4. We get 4 equals 4. It's true. Now, I knew it was going to be true, so I did put the equal sign. Over here, if we take 3 minus 5, we're going to get -2 equals, and I should have written -2 there. I better go back and check. Yes, it was x minus y equals -2. And we get a true statement. All right, let's get into some examples. I guess we'll do a quick summary here first. How do you find the solution to a system of linear equations? It's very simple. You graph both lines, and the solution will be the point of intersection. The point of intersection will be described by an x-coordinate and a y-coordinate. Those two numbers are the solution. If you need to pause this to write it down, go ahead, but I'm going to click through now. Okay, examples. Number 1, Nadia has currently saved $16 and her sister Lucia has $34. And what's happening is they both have jobs, and each day that they work, they're going to increase the amount they have in savings by a certain amount. And what Nadia is going to do is increase her savings by $5 per day, and Lucia is going to increase hers by $2 per day. And it says the girls are curious. They want to know if they will ever have the same amount of money. If so, how much money will that be, and on what day will that be? You can make a little note to yourself that Nadia only starts off with $16, whereas Lucia starts off with $34. The reason why there's a potential for them having the same amount of money on a particular day is that Nadia is adding more money every day to her $16 than Lucia is adding to her $34. Nadia adds $5 each day. Lucia is only adding $2 each day. So Nadia is adding $3 more each day than Lucia. And I'm sure there are other ways to do this, but we're going to do this by using a system of equations. So if we want to solve this, we have to set up a system of equations. And I'm going to say that y is the savings, and that will be in money, and x is how many days of work, and that's just in days. So how can we find out? This first one is going to be for Nadia. How can we find an equation that describes how much money she has? Well, all we have to do is take the current amount of money she has, which is 16, and add 5 times the number of days. Because each day that she works, it goes up by 5. When we take a look at, for Lucia, it's going to be her $34 plus $2 per day times the number of days. Now, I'm not giving you grid paper for this. There's a couple of different ways that we could solve this. We could use a table of values, but I'm not going to. I'm going to jump now to our graphing calculator. So what we're going to do is go to y equals in the top left corner. If you have anything entered in there, you're going to clear it. And I'm going to put Nadia's in for y1, which is 16 plus 34, 16 plus 5x. And for equation 2, which is Lucia, I'm going to put for y2, which is 34 plus 2x. Now, before we go into any kind of graphing viewpoint here, you need to understand that in this particular context, in this question, we're going to be graphing something where x is the number of days and y is essentially an amount of money, which means that we're going to start at 0 horizontally and vertically. And we have to use a little bit of common sense here. What we're doing is we're setting up kind of our maximum and minimum values of x and y using the information in the question. So the biggest amount of money is $34, and it's going to be going up and up and up and up and up. So I might take a guess that maybe we should go up to $100 on our calculator, and we're going to try that. What about the number of days? Well, we could use a little bit of common sense here. After 1 day, if I were to put the number 1 in here, Nadia's savings would be $21. And if I put the number 1 here, Lucia's would be 36. So it's clearly going to be more than one day. How many days do you want to try? I'm going to suggest we go up to 15 days. And if 15 days doesn't do it, if we're not happy with the outcome here, and I honestly don't know if we're going to be or not, then we can change the settings. So we have everything in the calculator. Now what we're going to do is we're going to go to the window key, which is right to the right of your y equals key. And when you hit window, it says x min, x max, and x scale. So the minimum x is 0. The maximum x, I'm saying we're going to try 15. The scale is just a number that tells the calculator where to put the ticks. So I'm going to change that to 5, which means when we do take a look at the graph, we're going to see a mark at 0, a mark at 5, a mark at 10, etc. Now what about y? Well, the minimum y is 0. The maximum I'm saying is 100. Why 100? Because I'm just going to try it. It seems like a reasonable amount. And the scale I'm going to put at 20. The scale doesn't really matter. It just makes the graph more presentable. I'm going to see a tick at 0, 20, 40, 60, 80, etc. And now I'll double check my entries for y. Let's just take a look here. 16 plus 5x, 34 plus, look at that. Always a good idea to check, plus 2x, graph. Now, I honestly didn't know if that would work or not. But if it didn't, if the point of intersection was going to be off the screen, then we could have increased the x and y maxes. Now, how do we determine the coordinates of that? Well, what you need to do is go to the Calculate menu of your calculator. And if you look at the row of 5 buttons at the top, there's a button that says Trace. If you go second Trace, you're in the Calculate menu, and I'm sure that you can figure out which of these options we want to select. It's Intersect. And to solve this equation or this problem now, all we have to do is choose Intersect, and it'll say first curve, and if you take a look at the top of the screen, it says Y1. So we're on Y1, and just hit enter. It says, what do you want to use for the second curve? Well, we're on Y2, let's hit enter. And then it always asks you to guess, and you don't need to guess, just hit enter a third time, and you can see 6, 46 is a solution to both of these equations, because it's a point that's on both of these lines. So the solution to this problem is, yes, on day 6, was it 6? Each person will have $46. Now you could have just done that with a table of values. You could have said the following. Day 0, 1, 2, 3, 4, 5, 6. Y for Nadia starts at, I think, $16. Y for Lucia starts at $34. Nadia's goes up by $5 each day. And now I'm only stopping at 46 because that's where my table went to. If I decided to go to 7, this would be 51. I'm adding 2 to the 34. Every day I'm adding 2 to Lucia's, so that becomes 38, 40, 42, 44, 46, jackpot. All right, let's take a look at the next question. Solve this system of linear equations. And I'm going to take back what I have in your handout. Let's use our graphing calculator here. You should be able to do it on paper, but we're going to use a graphing calculator. First of all, equation 1 here can be written as y equals negative 5x minus 1. All I've done is I've subtracted 5x from both sides. For equation 2, I can subtract x from both sides. And equation 2, I'm going to get y equals negative x plus 3. So let's solve this graphically. So for y1, there we go. I'm going to put negative 5x minus 1. For y2, I'm going to put negative x plus 3. Make sure I've entered them correctly. Negative 5x minus 1, negative x plus 3. My recommendation to everybody is, unless it's a word problem, like Lucia and Nadia's money, always go to the zoom key, which is dead center on the top row of your calculator, and choose standard, which is number 6. There's line 1, there's line 2. To find the solution, all we have to do is go to the calculate menu, choose intersect, enter 3 times afterwards. So negative 1 comma 4 is the solution. What is the solution? X equals negative 1. Y equals positive 4. Anyway, that's the solution to number 2. If we use graphs, if you want to do it using a table of values on your graphing calculator, all you do is you go to table set, which is second window. So you're going to choose second window. I prefer to start at negative 5 and go up by 1 automatically. What this is going to do is generate a table of values. I don't need to write this down, but I feel that I just want to. That starts at negative 5 and goes up by 1 each time. And it's an infinite table. You can scroll up or down to suit your needs. So when I do that and I go to my table, which is second graph, I'm looking for the place on this table where we have the same y coordinate. So y1 and y2 are not the same when x equals negative 5. They're not the same when x equals negative 4. They're not the same here. They're not the same here. But they are the same when x equals negative 1. And that was the solution that we got when we solved it graphically. We happened to see that they were equal at negative 1, and the y coordinate there happened to be 4. So that's the solution. Let's do one last example. Let's not verify. I guess we can. It'll only take a minute. Our x coordinate was negative 1. Our y coordinate was positive 4. So I put negative 1 in for x and 4 in for y. What do we get? Negative 5 plus 4. We're happy here. The left side and the right side are equal. Negative 1 for x, 4 for y. Negative 1 plus 4 is 3. Again, we're happy. So let's solve this one using our graphing calculator, and then we're done with the lesson. The first thing you need to do is rearrange each of these equations for y. And since y is positive here, I'm happy with that turn of events, so I'm simply going to subtract 3x from both sides. Over here, y is positive. I'm happy. I'm going to leave the 2y there and subtract x from both sides. And now I have to divide everything in equation 2 by 2. Because on my graphing calculator, I don't have the opportunity of entering what 2y is. When I hit the y equals button, it says y equals, not 2y. So I have to get that y by itself. Negative x over 2, also known as negative 1/2 x, minus 6 over 2, which is 3. So this is equation 1 that we can graph line 1 with. This is equation 2, which we can graph line 2 with. I think I'm going to do the tables first. We did the graph first last time. Let's try the tables first this time. So negative 3x plus 2 and negative 1. We've talked about this before, I'm sure of it. You do not need the brackets around the negative 1 over 2, but I like the way it looks better. Negative 1/2 x and then minus 3. Just double check that I'm entering those correctly. Yep. So now let's go to the tables. I don't need to reset my settings there. I'm just looking for a place where the y coordinate is the same. And by the way, if I suspect it's back around negative 6 or negative 7, I can scroll over to the x column and I can scroll up and down as much as I want to. But you can see these y coordinates are getting further apart. I want them to be closer and closer together. There we go. There's the solution. When x is 2, when x is 2, y is negative 4 for both. So the solution is negative 2 comma negative 4. If you want to do it graphically, you can just graph this instead. There are the graphs. I can choose the calculate menu, intersect, and then enter, enter, enter. And you can see it's x equals 2, y equals negative 4. Hope that lesson made sense. It's pretty straightforward. Just be careful to make sure that you enter things properly in your graphing calculator, and you should be fine. There are some practice problems on page 427 of the text. I hope that made sense. Have a great rest of the day, and we'll talk to you later. Take care.